I have been doing a good bit of work on some challenging customer relations issues on testing and mechanical testing, and had gotten some background on test uncertainty. And Dave thought it'd be useful to share that with you as member companies. And so if we look, we have a big data set from our members who've contributed carbon steel. And so I went to our data set and took all of the material that qualifies for WCB according to both the composition and the range of ultimate tensile strength. So that lets me look at yield strength in terms of material that is in that category, but doesn't eliminate all of the things that don't meet the yield strength minimum. And so this graph is from our Old Orange Handbook, and it shows an early study 40 years ago about the distribution of properties we'd expect in yield strength for the WCB type material. And you can see it's from about 40 KSI to about 55 KSI. This is a normal probability plot. If you're interested in doing these, if you send me a note, I can send you it. I downloaded it off the web. Basically, if you rack and stack your property data from the smallest to the largest, it gives you a probability plot. Z is how many standard deviations you are from the mean. So the mean is on this line here. So the mean value is something on the order of 47. And then it measures how many standard deviations you are. So if you're more than 3 standard deviations away, that's probably crappy data. And so if you're more than 3 standard deviations away, that's probably crappy data. You can see that this line here assumes that it's a normal distribution. And so the data we have from our members is not a normal distribution. And so one would assume that this data is probably mislabeled because I took all the data that was labeled normalized and tempered, but there's no reason that the foundries who submitted the data would have been that careful in validating their information. And so if they were making LCB and meet the properties, it may have been mislabeled as normalized and tempered. And that would make sense in terms of having this much higher yield strength curve that goes straight up. And so you can see that 36 is a normal value, and you can see that we get a little compliance bias right here at the bottom. One of the challenges is the measurement system creates a certain amount of uncertainty. So just to give you some sense of scale, for a 505-inch diameter bar, which is the most common bar, the reason we use 505 instead of half an inch is because when you do the math, that means you get 0.200 square inches, which means it's really easy. You multiply the load by 5, and that gives you the strength. And so that makes it really easy to do it. Before we had calculators, and we just had to do all that manually, and that's why we use a 505 bar. 1% of that is 2 thousandths of a square inch, and so that gives you a diameter of 25 thousandths of a square inch reduction. And so 1% error in yield strength from a diameter error of 25 thousandths of an inch. And so you can see it's a real problem. And so when people talk about a 1 KSI or a half a KSI difference, those are well within the measurement of yield strength, ultimate strength, and reduction in area. You get the same kind of thing when you look at the elongation. And so with elongation, you get the same kind of, ordinarily 22 is the minimum for that. They cut it off. This was a 1025 they looked at, and they said the minimum was 24, and so they cut their data off. I didn't cut our data off. I used the ultimate strength to create that data set. And so this gives you the data set, and you can really see the compliance bias here. And so what is a compliance bias? Compliance bias is when I fail to meet the specification and I look at that measurement or I remeasure it, and when I do, I know that I'm really close to meeting the specification. So I want to make a really good measurement to make sure I don't mess up the measurement and say that the material doesn't meet the qualification. So even if I am spectacularly honest and really critical in terms of making the measurement, I am going to frequently find that with a remeasurement, if I'm careful, that measurement will put me back into compliance. So I have an incentive and a real bias towards measuring things so that they're in compliance with the specification. So if I was really going to set the minimum capability of this data set, I would get rid of everything under 3 standard deviations, and I would eliminate all of the minimum specification stuff. But this also means that it's really the specification takes into account the distribution of properties. And so it says that if I really get a measurement that's down here and I remeasure it and get a measurement that's up here, the measurement up here can count for it, because I'm really, this measurement that I took to begin with may have been in this part of the distribution, and if I remeasure it, I get higher. And I really have 2 different sources of this distribution. One is the inability to measure exactly the same piece of steel twice and get the same number. That's test uncertainty. And then I've got variability in the material itself. Even since I broke that bar, I have to use a new bar, and that new bar comes from someplace different, and that different location will have slightly different mechanical properties. And so in the ASTM E8 standard, I only measure elongation to 0.5%, because I only measure the 2-inch test bar length to 0.01 inch, but 1% elongation is 0.02 inches. And so I'm really only measuring to a 0.5% elongation. And that's why you see this stair-step behavior here that you don't see here, because we get really nice measurements for our loads off of the equipment. But in terms of elongation, at least for steel, we take the instrumentation off so we don't break it when the specimen breaks, and then we put the specimen back together to try and get that measurement. Reduction in area is a more meaningful measurement of plasticity on the one hand. On the other hand, it has even bigger problems in terms of the ability to measure it, because we don't end up with a fracture that's a cylinder. So how many measurements do I take? And not only that, I don't get a reduction in area in the perpendicular direction. So I get a shear often, or a non-planar failure path. And so it becomes really difficult to find the minimum area in order to calculate reduction in area. So the ductility measurements are really somewhat problematic in terms of the measurement itself. So if I take all the data, you can see that problem. You can see both the problems I talked about. If I do ultimate strength versus yield strength, I normally get a really nice curve with a tight fit. And you can see that here, but clearly all of that property data that had high yield strength is up here, which shows that I really have 2 populations. So if I was really going to push this, I would have to go back through the data and eliminate all of this, and I'd get a really nice curve where, exactly as I'd expect, the yield strength will go up as the ultimate strength goes up. But here, when I plot elongation versus yield strength, I expect a 1/x kind of curve. I expect it to come down. And even if I hold my mouth right, I can't make that come down, even though that's a huge range from 40 to 80 KSI. And yet at 80 KSI, I'm having the same basic ductility I have at 40 KSI. And that just is shows you how problematic the measurement of ductility is. And when we have one other factor that we'll see in a minute, that oftentimes if I have any feature in that cross section, then I'll get low ductility. So this is, I have all the references at the next to the last slide in the presentation. So you can, with internet links. So if you're really nerdier than I am, you can go to these reports like this Code of Practice 07, and it actually allows you to calculate for a particular measurement what the test uncertainty was for tensile testing. They've also done it for Sharpie V-notch. ASTM evaluated test uncertainty. So in ASTM E8, they have a series of tables on precision, and precision is really a measure of test uncertainty. So the S little r is the coefficient of is a standard deviation for repeatability. S little r is repeatability. S cap r is reproducibility. This is within lab. This is between lab. So these would be the numbers you would use if you were talking to a customer who was measuring the same test bar you measured, but of course he can't. So you have not only this problem, you also have the other problem. So if we really wanted to do something in ASTM, just like we have product analysis tolerances, we probably ought to have mechanical testing product analysis tolerances, which would say that if my customer gets a value that is within 3.5 for an ordinary steel, 3.5 KSI of the minimum requirement, that probably should be a pass. And Caterpillar used to use, I think, 80% of the yield strength as their main criteria. And so if they mainly buy stuff that's 50 KSI yield strength, 8% would be this 4 KSI, 95% confidence for reproducibility. And so this is a chart that you can use in discussions with customers about test uncertainty and tensile testing. We also did this for the ASTM A487 from our database. And you can see here that outside of the 3 standard deviations, you get a nice linear plot for both. 15 KSI is the normal minimum for this material. We also have data because we're trying to predict properties in actual castings looking at test blocks. And so most of the data we have comes from keel blocks because it was intended to qualify the heat, not to determine the properties in the product. We can use test blocks when it's critical, and in test blocks, you normally want the quarter T, thinking the quarter T gives you the most representative properties. So if I look at this 4x4x4 test block that we got from Harrison Steel of 8630, they were making it for the 115/95 15 KSI material. You can see that they, in their standard test, got the 15 KSI minimum. They have 42 reduction in area, and they got the 116. So they really did meet the requirement in the standard test bar, which came from this corner. Now, we would expect then that like item 6 would give us good properties, but it doesn't even meet the requirements. And yet all of our data from our original work says that the biggest difference is drag to cope, not surface to center. And so if you look at the drag specimen, number 5, you get the best properties, high ductility, high qualification. If you look at number 1, you get pretty lousy properties because you're right under the riser. Number 1 has some shrinkage in it, as you can see here, whereas number 5 has almost no shrinkage in it. Number 7 is really clean, and it also has really good properties. So it's actually down in the corner, in the bottom. So the highest cooling rate, lowest material gives you the best properties. So if you have to pull a specimen from a casting or a test block and you're trying to meet the properties, it's clear that the place that's going to have the optimal properties is going to be in the bottom. The other thing that's really interesting to see is the range of properties you get. You get from 95 to about 115, or about a 25 range in the yield strength. And so for the ultimate, without this one specimen that has a lot of missing material, you get from 3 to 16, or 3 KSI range. Both of those are well within the kind of test uncertainty or reproducibility. So you really got the 2 factors you have to look at when you're trying to understand variations in tensile test properties. One is the location of the specimen, and the other is the uncertainty in the test method. You can do the same thing with Sharpie V-Knot. So this is from that same old orange handbook, and you can see that the range of Sharpie values is on the order of almost 30, 25 foot-pounds difference between the lowest value and the highest value, and yet the average values are relatively well behaved. And you can see the same kind of distribution here. Sharpie was always problematic. And so for the Sharpie specimens, when they started looking at the Sharpie test to standardize it, the challenge was that the Sharpie no one was sure that two different Sharpie machines could even give the same results. So NIST, the National Institute of Standards and Technology, did a huge program to try and understand how reproducible the different machines were. And with careful maintenance, you could get that with plus minus 5% if you were measuring over 20 foot-pounds. Under 20 foot-pounds, they give you a plus minus 1 foot-pound, but that's misleading because most people believe that are technical believe that once you get under 20, and certainly once you get under 5, it's not clear how meaningful the Sharpie value is because of friction in the machine and variations in the test. But once you get above 20, then it's a plus or minus 5%. So if you're within 5%, that probably is a meaningful amount of, probably you are within the test uncertainty. So they also, this group for the Europeans also for their code of practice, identified all the variations that give you the uncertainty, test uncertainty in Sharpie V-notch. So for Sharpie V-notch, it's pretty interesting because I can actually take the data that I have and take the highest value and the lowest value from 3 specimens that are supposed to be in the same location. And for the 8600 material at minus 40 degrees, if I do that, I get at least 10 foot-pounds difference typically between the maximum and minimum from a set of 3 specimens. If I do that for the HY80 material with an average of 80 instead of an average of more like 60 or 50, I get 20 foot-pounds between the highest and lowest value. So that gives you some indication of the uncertainty involved in making the CVN measurement. Part of that is how small of a specimen you're really looking at. For a 505 tensile test with a 2-inch gauge length, you're only looking at 3/4 of an inch cube of steel that you're measuring, which is really small. So one of the things I forgot to point out up here is that the large specimen gives you better properties on typically than the small specimen. And that has to do with the fact that in steel castings, our second phase contaminants, whether it's microporosity or inclusions, are on the order of a millimeter. And if I say they're on the order of a millimeter, a half of an inch is 12.5 millimeters. So I'm already, if it's 1 millimeter, I'm almost 10% of the cross section. But when I'm at a 1/4 inch diameter, then I'm already using up to 1/4 of the specimen with that inclusion or porosity. So in impact testing, I have even a bigger problem because I'm only looking at an 8 millimeter by 10 millimeter plane. And so if I get a 1 millimeter feature in there, I'm really compromising that cross section. So one of the things we need to think about is looking at things like dynamic tear as a better, more meaningful measure of toughness. So with that, these are the references that I have. I'm happy to respond to any detailed questions you might have via email or something. And when you have conversations with customers, we're always willing to get involved in that customer conversation, because if you're within 1 or 2 KSI of the minimum yield strength or the minimum elongation, then ordinarily with some additional analysis, the customer can offer you a waiver. So we have an ongoing problem within our industry. We do remeasurements and determine that the original test was in compliance, which is perfectly legitimate. But then when we get close and it really did just barely fail to meet the specification, then the ordinary practice that we need to pursue is to get a waiver from our customers saying that the material is acceptable even though it failed to meet that minimum requirement.